Investigations on the thermal end. Dynamic mechanical properties of rattan cane fiber, Calamus Deeratus, filled epoxy composites. Abstract: in this study, the dynamic mechanical and thermal properties of rattan cane fiber reinforced epoxy were investigated. Varying fractions of the composites with 530 Wt% fiber content and stoichiometric ratio of the epoxy/hardener, 2:1, were fabricated using a compression molding machine at 130 C for about 10 minutes. The laminates were cut to square shapes, 15 x 15 square centimeters, as test samples. FTIR Agilent technology was used to characterize the chemical structure. PerkinElmer TGA 4000 was used to study the heat flow characteristics. SEM model Phenon proximity was used to study the surface morphology. The results showed that the treated fiber had improved facial adhesion. TGA results showed a decomposition temperature for filler to be at 310 C. SEM shows best microstructure at 10 and 15 Wt% of fiber, while DMA results depicts best combined values at 25 Wt% fiber loading for storage and loss moduli and tan delta. Keywords: Calamus Deeratus, epoxy, DMA, thermal properties, dynamic mechanical properties. Introduction. Composites of natural fibers and polymers are finding places in many industries, particularly in the automotive industry that demand materials that have low density, low cost, thermal and dynamic stability. Since many polymer matrices as well as most natural fibers have these characteristics, composites based on them usually show excellent specific properties. 1. Various types of lignocelluloses fillers have been exploited, including wood flour, henequen, kenaf, hemp, sisal, flax, rice husk, jute, and others. 2, 3, and 4. Fiber-reinforced composite materials use fiber materials to mechanically enhance the strength, elasticity, and physical appeal of polymer composites. The extent to which strength and elasticity are enhanced in a fiber-reinforced polymer depends on the mechanical properties of fiber and matrix, their volumes relative to one another, and the fiber length and orientation within the matrix. 5. A great variety of organic fibers obtained from cellulose-rich plants have in recent years not just being investigated but effectively employed in varying engineering composites. 6. Despite the advantage of organic fibers, the use of organic fibers as reinforcement agents, particularly in hydrophobic polymeric matrices, have several drawbacks such as poor wettability, incompatibility with some polymeric matrices, and high moisture absorption by the fibers because of the hydrophilic nature of organic fibers. Other factors bedeviling the proper and effective harnessing and utilization of organic fibers is its degradation at relatively low temperature due to the presence of cellulose and hemicellulose. This early thermal degradation limits the allowed processing temperature to less than 200 degrees Celsius and restricts the type of thermoplastics that can be used with organic fibers to some commodity plastics such as PE, PP, PVC, and PS7. They get sticky, crack, and shiny and melt in heat and humidity. Fibers reinforced composite materials undergo various types of dynamic stressing during service, mainly in automotive products, and the dynamic mechanical properties of these materials need to be investigated. The organic fiber used in this research is the rattan cane's fiber. Rattan has 13 genera with over 600 species. 4 of these genera are endemic to Africa in the tropical rainforest regions. The species in Nigeria in descending order of availability are Calamus Deeratus, Aramispida macrocarpa, Onchocalamus manni, and Lacosperma secundiflorum. L. secundiflorum, C. Deeratus, E. macrocarpa, and O. manni having average stock densities per plot of 100 square meters of 6, 22, 12, and 18 clumps respectively. Calamus Deeratus is the most abundant species in Nigeria with small stemmed diameter ranging from 7.2 to 17.8 mm. Rattan canes are mainly from wild stocks, and cane furniture/handicraft weavers form the bulk of cane users. Other uses of cane within the study area include, as cane for flogging, ropes for tying hides to drum frames, fish traps, loop for climbing palm trees, as food sources, and in medicinal applications for making artificial bones. 8. This paper examines the properties of rattan Calamus Deeratus and its application as organic fiber. The determination of the properties of rattan was conducted according to ASTM standard with a suitable modification. Composites were developed from epoxy and rattan cane fiber, treated with NaOH, using compression molding process. 2 materials and methods. A. Materials. Epoxy Li 556, bisphenol A diglycidyl ether, resin is used in this study due to its wider range of applications, its characteristic high adhesion, mechanical strength, heat, and corrosion-resistant abilities. 9. Hardener used is Hi 951, IUPAC name, NN-bis, 2-aminoethylene 1,2-diamine. Sodium hydroxide, NaOH, distilled water, and processing oil were obtained from Rovet Chemicals, Lagos State, Nigeria. Rattan cane was obtained from the surroundings of Owerri in Imo State, while foil paper was obtained from Pascal Scientific, Lagos. B. Preparation of the composites. The cane fibers, Figure 1, were soaked for 4 hours and washed in water to remove the adhering dirt and peel the bark. They were dried in an oven at 70 OC for 6 hours. After drying, they were cut with Waring blender to reduce the length of the fiber to 2 to 4 mm. Fibers were pre-treated with alkali using 5% NaOH solution for 4 hours. 4 hours. After pre-treatment, the fibers were washed with distilled water until all untreated sodium hydroxide was removed. After washing, the fibers were pre-dried, and oven-dried at 80 OC for 4 hours. The fibers were bow milled for 12 hours to get a sieve size of 70 m prior to compounding. The biofiller, rattan cane, was mixed with the epoxy by stirring at room temperature in a glass beaker with the help of suitable glass rod. Hardener was added into the beaker containing mixture at a time of stirring. With proper stirring for 10 minutes, uniform mixing of the reinforcing agent and the polymer matrix was ensured and they were poured into a suitable mold. The fiber content of the composition was varied from 5 to 30 Wt% at 5 Wt% interval, while the matrix, epoxy and hardener, content of the composition used was in a ratio of 2:1 as shown in the table 1 below. See characterization. The FTIR spectra of fiber were recorded in the range of 4000 to 600 cm1 at a resolution of 4 cm1 using an FTIR Agilent technology spectrometer. Thermogravimetric analysis, TGA, of the biofiller samples were studied using PerkinElmer TGA 4000, Netherlands. The morphology of the samples was studied using scanning electron microscope model Phenon Proximity manufactured by Phenon World Eindhoven, the Netherlands. Sputter coater used is Q150RES manufactured by Quantum, England using 7600F at an accelerating voltage of 5.0 kV and magnification of 1000. The dynamic mechanical properties of the samples were studied using model DMA242E Artemis. Specimens approximately 1 mm thick, 3 mm wide and 20 mm long were machined from a larger sample of cured laminate to evaluate the stiffness and damping properties of the samples. 3 Results and discussion. A. Characterization. The FTIR spectra analysis of the untreated and treated samples are shown in figures 2 and 3. Untreated rattan fiber spectrum in figure 2, A, shows O stretching vibration of cellulosic structure with peak intensity of 3302.4 cm1 indicating the presence of OH, H-bonded stretch of the alcohols, phenols compounds. This peak intensity tends to shift after sodium hydroxide treatment to 3377.0 cm1. The peak that appeared at frequency of 2970.0 cm1 indicated the presence of CH stretching vibration of cellulose/hemicellulose, which changed to 2922.2 cm1 after sodium hydroxide treatment 10. The C=O linkage of hemicellulose in the raw rattan fiber is exhibited by band of 1699.7 cm1, which changes after sodium hydroxide treatment to 1707.1 cm1. Peaking bands at 1602.8 cm1 and 1509 cm1 of untreated rattan fiber related to C=C aromatic stretching vibration due to lignin, which peaks at 1606.5 after treatment. The peak that appeared at frequency of 1360.5 cm1 indicated the presence of CH of alkanes. The peak that appeared at frequency of 1230 cm1 indicated the presence of CH, CH2X, stretch of alkyl halides. The peak that appeared at frequency of 1028.7 cm1 indicated presence of CN stretch of aliphatic amines. B. Thermogravimetric analysis. Thermogravimetric analysis, TGA, determines the thermal degradation behavior of fiber by measuring the change in the weight of the composites sample when heated in air. When the filler/compound is heated at low temperature, moisture and other volatile components is evaporated first. 48.62 OC-194 to 29 OC. Further heating of the filler will get part of it degraded and converted into gaseous product with corresponding weight loss, which is reflected in TGA curves 11. On further heating, all organic matter will be removed, leaving behind inorganic components in the compound. The TGA curve from the Fig 4 and 5 for the biofillers indicated a melting point of 194 to 210 OC, which also overlaps with the distortion of water. The decomposition temperature for the fibers was indicated to be at 310 degrees C. It may be observed that the decomposition peak is relatively a lower temperature as compared to that of native starch and other plants' fibers. 12. Biofillers are wider in size, covering more temperature range for complete decomposition of thermoplastic fibers, confirming the better thermal stability of thermoplastic as compared to native fillers, not mix with matrix. The decomposition temperature is at 310 OC, which appears as a glass transition, Tg. This behavior may be related by the TGA curve between 194 to 220 OC. The decomposition temperature was shown between 310 to 410 OC. Degradation of all polymer composites first degrade at the temperature peak started at 220 OC, which is similar to the degradation of lignin materials, hemicelluloses, cellulose, and lignin. Degradation temperatures are approximately 180 OC, 190 OC, and 200 OC respectively, as stated by the following investigations: 13, 14, 15. The decomposition temperature peak gives the highest decomposition temperature at 512 OC. It is known that degradation takes place at this temperature. See Morphology. The SEM micrographs in Fig 6, AD, show the percentage of fillers and its effects on the biocomposites. It can be seen that micrograph showed various level of adhesion. It can be observed that the samples have a smooth adhesion. It is very clear that the filler weight of 1025 Wt% increases the effective surface area available for wetting by the polymer matrix. It is achieved by increasing the fiber aspect ratio of length to diameter, by reducing the fiber diameter. The micrographs with a rough surface are a consequence of the matrix having higher surface energy and can improve the interface adhesion with the polymer matrix. The rough surface is made up of pits, which are circular holes of about 1 m of diameter. The presence of pits and global marks after chemical treatment is important for increase in the effective surface area. This also increases the roughness of the fiber surface and consequently improving mechanical bonding with the polymer matrix. The composites show more or less even distribution of the filler on the matrix, as the filler is not so viscous but tacky. As it spreads within the matrix, it tends to stick. The physical appearance of the composites is ash black/brown black and brittle. The brittleness properties increases with increase in the filler content. It may be suggested that as the filler was spread by mechanical agitation, it goes in between the epoxy molecular chains and branches and stuck, thereby destructing the hydrogen bonding between the intermolecular chains/branches of the matrix. This phenomenon is prominent as filler load increases. It is observed that they all have better physical and morphological appearances in terms of surface flatness and homogeneity than 5 Wt%, while the reverse is the case for higher ratios. Thus it will be expected that the mechanical properties will have a similar effect. The biocomposites of plant origin are more hydrophilic. D-dynamic mechanical analysis, DMA. Fig 7, AG, shows the outcome of the DMA/DTMA results. The dynamic mechanical analysis, DMA, depicts the stiffness stability of the composite with the increasing temperature, its glass transition temperature and its viscoelastic nature when stimulated by dynamic loading. The tests were carried out under the load stress of 150 kN/m2 slightly above atmospheric pressure. The amplitude of 60.00 nm, smoothing of 3E005/0.1 m and PF of 1.10 were maintained during the investigations. The curve shows the composite is stable under the dynamic loading, having zero strain, with increasing temperature at frequencies of 2.5 Hz, 5 Hz, and 10 Hz up to 80 OC before the onset glass temperature of 37.4 to 54.4 OC. The results of the investigations showed that Fig. 7, filler samples of 5.030 Wt% filler loading, composites, give a good outcome in their performances. It showed the most outstanding storage modulus result at the onset of 56.2 OC and inflation of 59.0. Storage modulus or in-phase component is the measure of elastic modulus of a material but not the same as Young's modulus. It has the second to the highest storage modulus at the temperature of 59.2 OC and though with a lower MPa of 239. It also has a glass transition temperature of 56.2 OC, glass transition temperature, sample become less hard as storage modulus decreases and tan delta peaks. Tan delta peak height is typically between 0.1 and 1.2. The onset can be taken to be the TG. The tangent delta 75.6 OC and peak of 0.910 while the change in length fall at 72.0 OC and -536 m. Figure 14, filler sample 5.00, has an outstanding tangent delta at temperature 7596.6 OC at peak of 0.910. Tan delta or damping is the loss of mechanical energy. Modeled by a dashpot. It has a change in length of 72.0 OC and -536.4 m. The variation in change in length may be attributed to the content of the filler introduced to the matrix or sometimes may occur as result of the thermal history. From the thermographs, the onset of storage modulus of the composite fall within the range of 37.4–56.2, while the inflation of the storage modulus of all composite investigated fall within the range of 41.4–58.2. The temperature of the loss modulus fall within the range 35.7 OC 56.6 OC, while the strength the samples fall within the range of 175–315 MPa. In tangent delta, the temperature range for all the investigated sample fall within 67.4 OC 75.7 OC while the peak of the samples fall within 0.718 1.388. The change in length of the composites samples investigated fall within the range of 65.5 72.0 OC and 374.4 to -536.4 m. While the glass transition temperature of the samples fall within the range of 37.4 OC 56.2 OC. From the results obtained, it can be noted that the combination of the thermoset matrix and the biofiller with the additives can yield a composites for domestic materials. For conclusion, a study has been carried out to determine the effects of rattan fiber reinforcement on dynamic mechanical and thermal properties of the composite. The FTIR spectra suggest replacement of hydroxyl bonds between the composites and partial ester formation for the fiber studied. The biocomposites were shown to have improved thermal stability with the application of suitable dual coupling agent than in their respective pure states. There is better adhesion of smaller particle size, which implies that particle size can affect adhesion and better filler performance as indicated by SEM micrographs. There is better enhancement in dynamic, mechanical properties for the treated composites samples compared to the untreated samples. The DMA curve also showed that the composites have higher glass transition temperature and better mechanical, stiffness, stability in high temperature under dynamic loading. Acknowledgements. The authors thank to Drive, Henry, and his team of technologists in Nihilist Zaria and Mr. Fidelis Nwanya for their supports in varying proportions and different capacities.